guys. So welcome to Stokely. So I'm working at Stokely, but I won't be the person talking first. We are very happy to welcome you for our Rust Meetup that we organize, I think, every few months. And so Yann was here at the last Rust meeting, wanted to talk about Rust. So that's, I think, something we have in common, of course. So Yann is a software engineer. It's very modest title at Twig, but actually is also the head of programming languages and compiler group. So you can ask him a pretty deep question about Rust afterwards. And the talk today, the name you might recognize ownership as a core thing of Rust, but not only Rust, uniteness as well, linearity and beyond. It's more like information theory aspects, but they are very linked to Rust, and this is an in-depth look at the genesis of Rust. So Yann, I leave you the floor, and thank you for being here.
Thank you. Thanks for inviting me, although I invited myself. But I want to talk a bit about the history of Rust and the history of ideas that made Rust what it is today, both from academic and practitioners, but I will talk a bit more about academic ideas because that's why I know best. And you may have heard like linear types or affine type system or substructural type system when talking about Rust. So I want to try to present where does this come from and how Rust fits into this landscape. I'll also give a bit other example of other languages that implemented similar ideas in different ways at the end. The goal is to give an introduction to those ideas and also give a bit of perspective that Rust is not just a bunch of rules and typing rules, but it actually came from good design, let's say. So Rust was created in 2006 by Green and Hoare at Mozilla. For 3 years, he was mostly working alone on this project. Then it was sponsored by Mozilla in 2009. From this period, he got other people on the team who were coming from different horizons. I think this is the thought of Rust is that they had people who knows like functional programming and type systems very well, but also like I think Steve Klabnik is coming from the Ruby world, so he brought a good user experience, like people using C and C++. At the first versions of Cargo were like, we don't need that, we have Make. And then they just loved it. But yeah, this idea that you can do better than Make. And also, I think Graydon and other people at Mozilla were very low-level programmers using C and C++. And I think have shot themselves in the foot many times with those languages. So then, in this period, it was a different language every 3 months, basically. It was very different from what you know today. There were built-in types for many different kind of pointers that were not like part of libraries. There was a garbage collector before 1.0. And I think it's important to note that they have very high-level design guidelines. They did not say we don't want a garbage collector. They say we want memory safety, we want fearless concurrency, we want zero-cost abstraction. And at that time, they thought that they needed a garbage collector for memory safety. And at the end, they found a way to avoid that, as we will see. It changed a lot. Then it was stabilized in 1.0, and we could say from 2020 a bit more, it started to really be used a lot in production and become a more mature language. So I will talk about a bunch of things. Some of the parts are like one slide, so don't fear about the number of parts. All the things introduce concepts and ideas that came from different origins, and I will try to explain how it relates to Rust. So my favorite is linear logic because, I work on that during my PhD, but also because it was invented for very different reasons, or we could even say it was discovered. So it was discovered by Jean-Yves Girard, published in 1989. And Girard is known among PhD students for being very opinionated. So I put a few of my favorite quotes. And really does like Tarski. Tarski, another logician from the previous century. So he was working on something called System F. It doesn't really matter. But the idea was that he was studying some concrete mathematical structure constructors that were like instances of some formal system. So you can think of a formal system as a thread in Rust, for example, and this was a particular implementation, that is a mathematical object that was obeying the same law. And he discovered something really interesting in this specific model, which is that functions were a bit more fine-grained than what he had in the system originally. In particular, there was this notion of a linear function, which are functions that somehow can use their argument only once, or how we say that. This is a very strange logic when you take it as a logic, because it means that once you prove something, you may not use it twice sometimes, which doesn't make sense for logicians, right? If you prove that, I don't know, you can decompose a number into prime factors, you can use this fact as many times as you want. It's a fact, it's true forever. In linear logic, it's not always the case. If you're a linear proof, you cannot use it so much your argument more than once. So far, it's just a strange logic. I just put a little illustration, but interestingly also, it means that you have two disjunctions, which is or, and two conjunctions, which is and, but it's another story for another time. Where it becomes interesting is that there is something in theoretical computer science, which is called the Courier-Word-Lambek isomorphism or correspondence, which says that basically the act of proving something is really similar to programming. So as an example, in logic, the most basic principle is called modus ponens, which is if you prove that A implies B, and you proved A, you can deduce B, right? In programming, that corresponds to function application. If you have a function of type A to B, and you have an element of type A, then you can get an element of type B by applying this function. But it goes beyond that. It's really a deep correspondence and not just a vague idea. There is a very concrete mapping from a whole family of logic to a whole family of functional languages. And when you put your your Courier-Word glasses, linear logic becomes a language where, as I say, a function must use its arguments exactly once. And yeah, linear logic is about resources. You can duplicate and erase, but you must do it in a controlled way. Maybe that reminds you something. There are things in real life, not theoretical computer science, that are also obeying the same law. So one is memory, for example. In that once you've dropped memory, for example, you cannot use it anymore. You should not drop twice. Or similarly, you cannot keep a copy or a pointer to memory that has been dropped before. And there are other examples, filehandles, also once you close it, you should not use it anymore. You should not duplicate it. Communication protocols. And if you look at Rust and you forget about borrowing and lifetimes, the core system of ownership and move semantics obey more or less the same law, right? If you have a function that takes an argument, an own argument, and you call this function with another own value, you cannot call it again, or you cannot do something else with the arguments that you've passed. So, in that respect, Rust is, this part of Rust, let's say this subsystem, is more or less, is really close to linear logic. So if there are experts in the room, it's not entirely true because there's no bang. But anyway, it's not exactly the same because we can still drop something in Rust. You don't have to call a function on V. You could just not use it. So it's called a fine, but it's the same, it's just a variant of linear logic. Okay, so now I talk about ownership, but what about borrowing? If you have like Rust without borrowing and lifetimes and just ownership, it becomes quite tedious to do mutations, basically. Often in a linear type system, when you give something to a function, you cannot use it anymore, but if you want to push to a vector, once you push, you might want to push something else. So if we wouldn't have borrowing, we need to do something like that, where each time you need to return it from the pushing function, get it back, return it, and so on. So for those reasons and other, Rust lets you use borrowing. But first I will make a detour to something called uniqueness. So yeah, as a Summary, linear logic was introduced for a very different reason. It was not a type system for programming language. But it turns out that in fact it's useful for memory and other things. And part of the Rust type system is linear. Uniqueness typing is a similar idea, but a bit different, as we will say. I don't remember who introduced it exactly. It's not the clean language, but it's a bunch of papers, but it is known to be used in clean. So clean is not very important, but it's a language that is lazy, like Haskell, for those who knows that. Means that your arguments are not evaluated right away, but only when they are needed. And the thing is that with those languages, it's quite difficult to do anything like, it's really hard to manage what we call effects, like printing, writing to a file, because there's no order. You cannot guarantee that this will be printed before the other. But that's not very important. What is important is that they had a bunch of problems that was this time related to, programming, actually. And they introduced this uniqueness typing. So in clean, a unique type is a type that is guaranteed to not have been duplicated or aliased before. And in fact, this is precisely the guarantees, for example, of mutable borrows in Rust. When you get a mutable borrow to a vector, for example, here to push it, to push an element to it, you are guaranteed that nobody else will have an active other mutable reference or immutable reference or whatnot. And so borrowing is really like uniqueness typing. What's the difference with linearity? In fact, the two are dual in some sense. And indeed, borrowing cannot be a phrase in pure linear logic. So one way to see it is that linearity, if you are a linear function, linearity is a constraint on the code. An example in Rust is that if you take fn once as an argument, a closure that you can call once, it is actually fn once is actually a linear, is the same idea as linear. The constraint is on you. You can only call it once. You cannot call it twice. The caller or the person implementing the fn once can do whatever they want. And also, linearity is a promise about the future. In a linear task system, you don't know anything about what happens before. It can have, maybe the thing has been duplicated 10 times once it arrives to you. So it's really a constraint on the coding. Uniqueness is a reverse. If you take a mutable borrow as a function, you have no constraints. Actually, you can do a lot of things. You can split it. You can make another mutable borrow. However, the person calling you has a constraint. They must guarantee that what they give you is unique. So, for example, they cannot call you if they have only an immutable borrow to something. So it's a constraint on the caller, and it's a promise about the past. Once again, you can split off a mutable borrow, but it is guaranteed to not have been duplicated, at least for the time it is alive, by the caller. And in fact, in Rust, we use nmut, but Nico Matsakis, one of the core team member, argues that we should really call it unique instead of mut, because it turns out that mutability is one of the use cases, but really the property that mutable borrow give you is that something is not aliased. And what's really remarkable about Rust is that it combines the two. As we said, the move semantics ownership is more like linearity, and it's not entirely true because of bugs and so on, but let's say. And borrowing is about, borrowing is uniqueness. And thanks to that, it is, to my knowledge, one of the first concrete type system that is able to guarantee both, to guarantee memory safety and to avoid garbage collection. Without that, I don't know how to do that, in a sound way. And so uniqueness and linearity were ideas that existed before Graydon-Hall was aware of them. It tells that many times. But I think the fact of combining the two to get that kind of features is really one of Rust's success, I would say. And a very important point is that all those things, linearity and uniqueness, in the end, they relate to aliasing. And in fact, it is most of the time the property that you want. You want to know things about aliasing if you want to do anything. So if you're a compiler, if you want to optimize stuff, you must know about aliasing. All compilers like in C and C++ do actually this kind of analysis. It's just an approximation. They don't have a type system, but they do alias analysis to try to deduce interesting things. But it's nothing like nowhere near as powerful as in Rust, where it's guaranteed by the type system. So aliasing is really an important property for soundness. What's interesting, though, is that in Rust, the application of linearity and uniqueness is not only for memory safety and garbage and the absence of garbage collection. And Rust also advertises itself as a language when you can do fearless concurrency. Well, it's true for threads. I wouldn't call it fearless when you do async Rust, but that's another debate. And there is an entirely different line of work, not entirely, but almost, where you can find the keyword ownership as early as 2021, which is whole logic and separation logic. But so their goal there for these researchers is to define a logic and reasoning rules that you can use to prove some properties about programs. So specific programs, right? If you get something that goes into Ariane or in a satellite or in a smart contract in the blockchain, and you want to make extra sure, like to formally prove that it never crash or that it never underflows or overflows. So those kind of logic, the ones to do that either manually or assisted by a computer. And quite soon, they realize either for being able to perform modular reasoning, or also when you add concurrency, that they need something like ownership. Because it's basically impossible to reason about a program if in between two of your instructions, anybody else can do anything to your memory, right? It's just a world you cannot live in. So they introduced this notion of what they call ownership, and which is more or less like uniqueness. They say, oh, this is part of the memory I care about, and I want to guarantee that nobody else is going to touch it. And if it is true, then I can show that my program won't do stupid things, and then I can prove that it is true, and I get what I want. And I think, so this is why also it helps with concurrency in Rust, where it guarantees that you don't have any data race. And what's interesting is that, so they introduced that in a kind of formal logic, but I think it's also what you need as a developer, because when you're writing programs, I mean, I don't know about you, but you need to do some kind of, well, partial and wrong formal proof in your head, but you're always trying to think about, okay, what I'm doing is correct because this won't overflow, because I can unwrap, because, and in fact, you come to the same more or less conclusion that if you want to understand or write any concurrent program, you need to have a way to guarantee that nobody's messing with your whole memory all the time. This is just a very quick slide about C++. I'm not a C++ expert, but I want to emphasize that it's not only academic ideas or semi-academic like the one that came from Clean and so on. Ownership is also found in as early as 98 in C++ in the standard. So they came up with similar ideas. I don't really know the relationship between, because researcher knows about C++ and conversely, so I don't know who came first. Probably everybody's aware of everything and they more or less inspire one or the other idea. But yeah, ownership is there in C++ 98 as a auto pointer, which is some kind of a very bad box, if you wish. And the other thing I want to talk about is lifetimes. So lifetimes is something that doesn't come from, to my knowledge, previous work in the literature. It is used in C++ and also, once again, as a mental model for anybody who does C++, or C, like I'm taking a reference, how until when it is valid, will I cause like undefined behavior if I do that and that. And same thing as for aliasing. Compilers also, they don't tell you, but they need to reason up to some point about lifetime, or they call that liveness, but it's quite similar. So there are ideas that also come from C++, and they're not in the type system of C++, but they are still standard in the way I guess C++ developers need to their mental model in order to try to write that kind of language without dying inside. A very also quick slide on optimizations. What's the type system of Rust and all those kind of guarantees give you, well, safety guarantees. I think they also allow you as a user to reason better about your programs, but they also allow the compiler to do things that it couldn't do otherwise. And so here, for example, you have a function do stuff that takes a mutable borrow to some data somewhere. And what we do is that we assign it to one, then we call f. And let's say that f is unknown, it could be in another crate, or even it could be closure that you take. So the compiler knows nothing about f. Then you assign x to 2, and you call another unknown function. And then you assign x to 3. To my knowledge, in any other language, if the compiler doesn't know anything about f and g, it cannot ensure that they are not modifying x. So it cannot touch this program at all. However, in Rust, what's really powerful is that because it knows that x is unique and it's guaranteed by the type system, then f and g cannot touch x. Neither can they read x, in fact. So you can't just remove the two first assignments because they are useless. Nobody is reading x in between. And this can sound like a stupid optimization, but this is actually the kind of optimization that's kicking in Rust and in LVM, because what you do is that you write a program, you call some function on very specific parameters, and then Rust does what we call inlining. That is, it replaces sometimes the function with its content. And then your very specific parameters are propagated in the code, and those kind of things that you wouldn't write yourself, but actually arrive by a series of other optimization, become very important to compile efficient code. Okay, I've talked a lot. Any questions so far? Cool. So I will end with alternative implementations. I will try, okay, I have 5 minutes, but I will try to not kill you with too many information. But there are some alternative implementation of linear types or unique type or whatever you call them. So linear Haskell, for example, is, for those who don't know, Haskell is a functional programming language. It's quite old, actually. It's from the 90s. They've added, actually, people from Twig added a linear type to Haskell as an extension. So a paper was published in 2017, and it was merged in the Haskell compiler in 2020. Linear Haskell closely follow the original linear logic. What it means, why did they do that? Is because for some technical reason, it was much easier to retrofit on an existing language. It doesn't interact in a too-bad way with non-linear functions, let's say normal functions. And also linear logic has been studied for like the last 30 years. There's a lot of literature. We know it well. We are able to reason about it. So it's good. However, somehow you just get half of the type system of Rust. And in particular, as I said, with non-linear type, you have basically no absolute guarantees about aliasing. So if a linear function, you are sure that it won't duplicate something in the future, but the compiler cannot look at the type and say, oh, this value, I know it's not alias, so I can do smart stuff. So it's mostly used to write nice and safe API, but at some point, the person writing the library will need to do equivalent of Rust and safe to say, okay, trust me, this is actually linear. So I put an example, but maybe I will only go back to it if I have time. The second one I wanted to show is oxidized OCaml. It's also called OX OCaml. It's been developed by Jane Street. So Jane Street is a high-frequency trading firm, one of the biggest and most well-known industrial user of OCaml. And this is a kind of application where you want a real performance, like a smallest latency possible. And so they push OCaml to its limits, where sometimes they want to avoid garbage collection or allocation in general. And so they develop some kind of extension of OCaml. So it's published now, it's a fork that is public, which adds something called modes. I won't enter the details, but the idea is that you can attach to bindings modes that say how they can be used. And what's interesting about that, so there are no lifetimes, no borrowing. It's a bit less powerful, but what's really interesting about OXOCaml is that those modes are quite algebraic, right? It's not like about nesting, lifetime, and so on. You say, oh, this would be unique. This must be used once. They also added some other stuff, which is a bit similar to send and thank for multi-threading, although it doesn't correspond precisely. But so they have a bunch of modes, and there are also nice duality. If you need to take an argument which is once, in fact, when your closure it's unique or something like that. So I think it's a nice system to think about as a developer, a bit more discrete and algebraic. However, as you see already, they start to be quite a bit of modes. And so in their paper on data race freedom, I find already the API to be not entirely easy to read and not even write. So it's I guess it's a different trade-off. However, it's entirely retrocompatible with existing OCaml code. And they do have both linearity and uniqueness. They have unique and once as a mode. Still, nobody has like Rust lifetimes, so it's not as expressive, at least on some axes. And yeah, might start to rub it. Last thing, what Rust, where does Rust fit? Well, I could say a lot about this, but I think one interesting thing that Rust is missing is that it's a fine, so it lets you at any point drop something implicitly. But it might happen that you don't want that. If you ever need what you could call distractors or drop with arguments, you need to drop something, but actually you want it to pass some argument or to get back a value. I know something that happened to me. I wanted to, we had a structure that was a bit complicated borrowing wise. So when we performed some transformation, we needed to take out some part of the structure to satisfy the borrow checker, some kind of cache insert into it, and at the end, put it back. However, there is no way with the current Rust system to ensure that we put it back, right? There is a hash map in it. If you drop it, but Rust wouldn't complain. And so what I would have liked here is to have a linear type system that say, actually, no, you cannot drop this. There's a blog post of Nico Matsakis about what he called must-move types, types that you cannot drop. It has application, we can talk about that later, but for async drop, for example, it will make the async drop proposal easier to implement. And some work by Thomas Bagrel, who is a colleague, and defended his PhD recently on how you could also use a linear type system for destination passing style. It's something that you do a lot in C, like you have a function, instead of returning a result, you take a pointer to an array, for example, and you feed directly. So in Rust, you could do that with, I don't know, maybe a unit or stuff like that. But it's quite tedious and it's not guaranteed that you feed everything. That's it. I think if you should remember something, it's that Rust is a mix of many different influences. And I think it's what it makes it a great language, both in terms of people and ideas. And this combination make it so that it can give guarantees in quite different domains, like, once again, memory safety and concurrency. It's not obvious that the same type system could give guarantees in both. And having a rich type system like that help both you reason about your code, but also the compiler. So hopefully make it able to produce better code. And that's it. Thanks.
We have time for a few questions, so like 5 minutes. Your question, guys. I have one question. I have multiple questions, actually. When you showed the IDS example, I think it's a very strong case for Rust, and even more so to replace the mute by unique. I think it really shows it would show better what's happening here and what's the real guarantee of safe rest. I have a question, maybe it's something you don't want to talk about, but I'm curious, how does that tie in with like side effect, like printing and stuff like that? How does that tie in with your explanation about the linearity? Like here, I feel like it's the mainstream Rust, but most functional language, they have like, they put under the rug the fact that at some point you will open the file on the file system. Like, is there something where there is like less guarantee in Rust?
So, no, sorry, I think I didn't understand the question.
Here, I think what's the statement about the fact that function f or g takes no argument is that like they won't access data because they won't have another reference to data in any capacity. But for instance, if we print something in the function and in f we print something as well, we are actually accessing an external resource.
Yeah.
And I guess we have less guarantee, or like what does the language propose for that?
You mean if there are other languages that could even allow to control that, for example?
Yeah, is it like something that's even feasible theoretically? Or?
Yeah, that's a very good question. So indeed here, the only guarantee we have is that it's about memory and it's about X. Everything else we cannot know. Well, in fact, Haskell, you have to do a side effect in a controlled way, to use monad, basically. They have the same problem as Clean, but Clean solved it with uniqueness typing, and Haskell introduced monad. And in Haskell, if you have something that doesn't have, if you can't see a monad in the type, like IO, you are guaranteed that, guaranteed as in Rust, except unsafe code, because you can use unsafe perform IO, but otherwise you are guaranteed that it won't perform effects, IO effects, or actually any effect. So there are systems like that, and there are even, I don't know if it's implemented somewhere mainstream like Haskell. Haskell is mainstream, it's more mainstream than some research language. But you even have some so-called effect system where it's part of the type of a function, like what kind of effect it can do. And those are like small sets. So for example, you can have effect print and write. And if you compose this function with other functions, the type system would be able to basically make a union of the set and give you another approximation of what the function can do as an effect. I think it's also called sometimes capabilities-based type system. Although I'm not entirely sure right now it's exactly the same thing, but same kind of idea.
So I kind of have a question just based on something you said a little bit earlier. With Haskell, if you don't have a monad in the type signature, you can guarantee that it's not going to perform some sort of effects.
Yeah.
Did I understand correctly that you made the same kind of statement about a function like f, for instance? Because that's not necessarily the case in Rust. You could have some sort of network call or something that's just entirely contained in that function f, or something that maybe reads memory or does something dodgy. But did I misunderstand when you said that function? Did you mean that function has to be pure specifically, or can that function be impure, i.e., have some sort of side effect?
No, so f and g can have all sort of side effects.
Yeah, exactly.
Yeah.
We don't know that because we don't know the type signature of f. Well, in this case, we don't know what happens in the function body of f. But okay.
Yeah, the only guarantee that Rust gives us, but it's already a lot compared to other language, is that whatever side effects f does, it cannot mutate x.
Yeah.
And it cannot read x.
Yeah.
And that's already enough for a compiler to do other things. But yeah, otherwise in Rust you cannot say anything about anything else about the other effects.
Maybe follow-up question, and this is actually something that I could probably look into a little bit afterwards. Is there some way to actually just read the self-programmed memory inside a function like f and then mutate the memory region of x, hypothetically?
If you do what, sorry?
If, for instance, inside this function f, there would be some way to read the memory of the program itself and then mutate some variables. It would likely have to be an unsafe function, I would imagine so. But
yeah, well, if you use unsafe, you cannot. Yeah, it's assuming that there is a UB, basically. Yeah, it's up to undefined behavior. Because you could just use row pointers and put it in another variable y and read it from f. So it's right. It's a good point. You have to. So it's for calls that is well typed, and if that could use unsafe code, actually you also have some kind of constraint on that unsafe code that has been formalized more or less in a series of papers. But yeah, if you have unsafe code that doesn't define behavior, then anything can do that.
It would be useful if maybe in the type signature of functions we enforce some sort of way to signal whether or not the function has unsafe code or has code that could produce an undefined behavior. But maybe this is me just talking to someone that already knows this stuff.
Yeah, you could do that. But in fact, affine behavior, it's not really useful because that's like the bottom line of everything. You say, I assume there is no undefined behavior, otherwise I cannot do anything. So, but yeah, you could mark, this is a very basic effect system when you would say this function relies on unsafe at some point. Also in Rust, because of the standard library, that would be a lot of functions, but you could do that, yeah.
I have a follow-up question that's a very, we're going to ping-pong question.
Let's go.
And we're going to smash and it's kind of an open question, so maybe you don't have the answer. Like you talked about the Haskell effect system, as far as I understood the name. It sounds very attractive. So it's a very open question, but do you know if there is a plan to that in Rust, or if that's even doable to have that in Rust? I think the unsafe thing, the problem is that it colors every function. Like if you use an unsafe function, everything becomes unsafe. But maybe I'm doing UV and we will never get out of it. But I feel like the effect function, effect system you're talking about in Haskell is less, like, would be more interesting. And do you know if there is a plan to do that in Rust?
So I think there is a proposal for an effect system, but I'm not sure it's related to typing. It's more
It's
about,
a bit different. It's
yeah.
like maybe a sync. You could have a function that is async when called from an async context, or not, or synchronous when called from a synchronous context. So it's not related.
But isn't there something like effect handlers proposal for Rust?
Maybe called something else.
Okay. But I think, as far as I can tell, the type system, that would be impossible to do it in a backward compatible way, because when you start to track effects, it's somehow, maybe it's not impossible, there is a way, but usually it's quite, it's a bit like async, it contaminates things, because now you have to track everything everywhere, and your old code have high chance of not passing the new type system, I think. But, yeah.
Yeah, I'm debugging with concatenate everywhere, so
yeah.
I guess it would be hard to be retro compatible. Well, any last question? No? Thank you again.
Alors,